Okay, so what I want to talk about here is more the dot connection from the food to the energy. And given that I was last on the schedule, I knew that it would be very hard to throw too much at you at this point. So I'm going to keep it simple and make 5 points about the energy-food connections. And I would say if you can remember one of those 5 points, you're probably batting above average. So you can choose which one you want to remember. Now there are many links, and let me just acknowledge that up front. And I'll trace out sort of some of the broad links, and then I'll go into depth on just one or two of them, two in particular. So we obviously use energy in food production at all stages of the food system. I had that picture of toast on the front. If you sit and look at a piece of toast, just think about how many times energy went into that production, and you start thinking about which of those steps use more energy, what type of energy. There's lots of points of energy input into the food system, which I'll cover. We also now increasingly use food in the energy system. This has been alluded to in bioethanol when we use corn or sugarcane for ethanol production. We also use canola, soybean, oil palm, other things for biodiesel production. So there's a very real presence of food in the energy system now, and I'll talk about that. But there are lots of other connections besides those more obvious ones, and I would think of those as very apparent, rapid connections. But there are lots of what I would think of more as slower, insidious or indirect connections via climate change. And so one obvious one is that the energy system, as you all well know, is changing the climate. And as the climate changes, it affects our ability or the way that we produce food. Maybe not an obvious point, but trust me, energy and climate has an indirect influence on food. I won't talk about this. This is something we work a lot here at Stanford, but it's not something we'll dive into today. At the same time, our climate situation really influences our energy policy, and that's something that Mike and others were talking about. And really, we have to recognize that the food system as a whole has a fairly significant influence on the energy, on the climate system. This is not only via its use of energy, but especially in terms of greenhouse gas productions associated with fertilizers, associated with cows belching, associated with rice production. If you sum up all of those things and actually you add in deforestation, which in most places is driven by demand for food, you get something close to 1/3 of all greenhouse gas emissions now are from indirectly or directly related to food activities. And so if you think that if you think that climate places a constraint on energy policy, and you realize that food is influencing the climate situation, then there's those connections as well. But what I'll try to do in this short time is focus on these two red arrows here, the more direct links between energy and food. So I'll try to structure this around 3 questions. How much energy is used in the food system, then how much food is used in the energy system, and then I wanted to just offer a few thoughts linking back to some of the earlier talks about this revolution that we've seen in natural gas and what is that going to imply for the food system. And we've really just started thinking about this. As Mark said, it's been, the past 2 years we've seen this order of magnitude increase in well production and things like that. That's a blink of an eye in the academic world. We can barely get grants approved in 2 years. So we're just starting to think about that. Now, the first and maybe most critical point for those who don't understand the food system is how critical energy is as both a land and labor saving technology. So land and labor are basically the two biggest costs or biggest inputs to food production in most places of the world. And energy, both directly and indirectly through the production of fertilizers, is incredibly good at substituting for both land and labor. So if you compare, for example, the manual subsistence rice production activity with something like a California mechanized rice production, there's lots of differences between these systems, but a pretty significant one is the amount of external energy inputs going in, on the order of 30 times bigger for the modern system. But that has significant benefits associated with both how much land we need to produce a given amount of food. It's anywhere from, say, 5 to 10 times more food produced for a given amount of land. And especially in terms of labor, we can basically reduce by 2 orders of magnitude the amount of labor used for producing food. And you can argue whether is that a good thing or a bad thing, but I think empirically most people prefer not to be working in the fields. They prefer to be doing other things, and energy has really freed us up tremendous amounts of labor. And as we think about agricultural development still, so in the Center on Food Security, we like to think about this, we recognize the critical role of energy in getting that started. If you want to think about opportunities to improve food security, you can often do pretty well thinking about opportunities to increase the energy provisions, maybe with some of these new technologies. Some of these new renewables have very attractive features for remote areas, et cetera. It's really a critical pathway towards, or start on the pathway towards agricultural development. Now, when we look at, as you go through that process, and now we look at the world as a whole, we are very much a mechanized and industrial agricultural society. What does that mean in terms of energy use? Well, if you add up all of the pieces of energy, and I show here how it breaks out in terms of the different components of energy use, it's about half fertilizer, so about half of the energy is because we're using it indirectly to produce particular nitrogenous fertilizer, but also phosphorus and potassium. The next biggest chunk of it is actually direct energy use, either in terms of tilling fields, driving tractors, or in terms of drying grain with dryers. And then water pumping, Dick mentioned the tremendous amount of energy used to pump water around. That ends up being about 8% of the total energy use of food production. And then there's a little bit for other kinds of chemicals we produce. Add all of that together, that's 10 exajoules of energy. Some of you are energy buffs, but for those of you like me who are not, is 10 exajoules a big number? Well, let me give you a little bit of perspective. The 2011 earthquake in Japan was 1.4 exajoules. So it's a lot of energy. We're talking about 10 exajoules of energy, and any absolute measure is a lot of energy. Exa is, 10 to the, I don't know, 15th, 18th. But if you don't laugh at me, Adam. If you're comparing that to global energy use, it's actually pretty small. We're talking something on the order of 2% of global energy use is used to actually produce the food that we eat. So is it big? Well, depends what you compare it to. Now, I want to point out, that is the food production part of it. Our food system is a lot more than just the crop production or even the food production. So here's a study the FAO did recently to try to tally up all the elements of the food system. And so down here, this is expressed as a percent, but since you can read this almost as exajoules, I said it's about 10 exajoules for crop production, and it's another few exajoules for the other types of food we produce. You can see the other parts of the food system, in particular the processing, the distribution, the packaging, the transportation, the retail, and the cooking and the preparation adds a significant amount to that. So if you add all of that up together, now we're talking about 20% of the energy use is for things like that. And so if you think about the food system overall and you think about opportunities to reduce the energy use, it's often in the post-production phase. And a lot of that just goes into electricity generation or food preparation technologies, things like that. Okay, I want to just address also, when you look at this chunk, well, a lot of people say that, well, we should all eat locally because look at all of this processing and distribution is a big chunk of it. I just want to point out a lot of that is the packaging, a little bit, here I showed here, this is data from the USDA that I've plotted as broken out by the different components. This is now for a typical American, so many of you average together, not each one of you individually, but you can look where you would be on this. How much energy do we use for the different types of food items that we eat? And you can see the production elements are in green. And this just breaks out the post-production a little bit more cleanly. So packaging is actually significant in a lot of these, the energy it takes to produce the packaging, especially for things that are sold in glass, for example. Freight is in there, it's significant, especially for heavy things like your German beers that you drink. But it is, in terms of the post-production process, it's not that big. And then the retail part is pretty small. What's not shown here is the food preparation part. A lot of that is embedded in the processing part. If you're buying bread, loaves of bread, for example, that's been baked for you. But the point here is that the freight as itself is not that big. And actually, if you compare different modes of freight, it makes very little difference if you're shipping it in from Chile or if you're driving it in from Stockton. So this is a common question we get from students as well. Should we eat locally? And there may be reasons to eat locally, but energy efficiency is not really one of them. Now, the other thing that I think is often misunderstood about energy use in agriculture, is that, like a lot of other areas where we use energy, we've actually been improving in our efficiency of use. Energy is a cost of production. And actually, if you look at the US farm sector, it actually uses less energy today than it did in 40 years ago or so. And that's really tremendous when you think about, if I were to plot production growth on this, on a similar graph, it would have more than doubled. So we're actually producing more than double with less the energy. And part of that is we've gotten more efficient at producing fertilizers, which I told you was half of the inputs. We've gotten a lot more efficient at our use of diesel. We use less diesel on the farm, partly because we've gone to no-till systems in the US, for example, and on and on. So the important point here is that, as I told you, food production itself takes a small percentage, and that's actually not even a growing percentage as we grow food demand. But it's a critical part. It's just not a big part of the overall energy system. So 3 of the 5 points are summarized here, that in terms of achieving both high land and labor productivities, energy use is absolutely critical. That overall, even when you add up all the energy that crop production is using, it's pretty small. If you add in the rest of the food system, it's significant. And that over time, we've actually gotten pretty good at using energy in the food system and reducing the use. Now let's go in the other direction. So how much food is used in the energy system? And the answer is a lot. Now, Mark mentioned how rapid the fracking has developed. We can't quite compete with that in terms of the ethanol use, but it's almost as fast that it's really the whole landscape has transformed. This shows you where corn in the US has been used over time, and it's traditionally mostly for animal feed, and that remains to be true, except that we've grown from ethanol being a very, very minor player early in the 2000s, or what some people call the aughts. I still don't quite get that. Up into 40% of our total corn crop now is going to ethanol. It's a tremendous fraction, tremendous growth over time. So is 40% a lot? Well, what I think has been alluded to a little bit, but not really, is we actually get very little of our energy now from renewables overall, but in particular from biofuels. This is a plot of the overall mix of US energy sources. And if you look at renewables, it's about 2%. If you look into that slice and look at where biofuels is, it's about 0.8%. So the bottom line is here is we're taking 40% of our corn and using it for ethanol, and we're getting about 1% of our energy. Now, I'm not trying to indicate that that's not a good 40% use. There's lots of questions around that, and how else would you get that 1% of the energy, but it's a lot of food for a relatively small amount of energy. And this is true even if you were to, so what I did here was just say, magically, if you just suspended our need to eat food and you took everything that we eat and converted it into energy, what's the energy content of that food we eat? That's this little dot down here. About 30 exajoules is what we consume. If you compare that to global energy consumption, the point here is that there's really no way that our food system can supply a significant fraction of our energy demands. And that's especially true as you go forward, because energy demand is increasing even faster than food consumption is expected to increase. So 40% is not a lot in terms of the amount of energy it produces, but it is certainly a lot in terms of what it does to food markets. And you can think of food markets now as the tail on the dog of the energy markets, in the sense that we used to have some link between energy and food prices. This is a time series of corn prices in red and oil prices in blue. And you could see that we had blips in some that weren't followed. But for the last, let's say, 7 or 8 years, it's been remarkable how in step these markets have been. We've gone from a correlation of about 0 to a correlation of about 0.81. What does that mean? That means that if you care about food price swings, if you care about food security, the links between energy and food now are very significant from the food side of things, if not from the energy side. And finally, let me just talk about natural gas. So this is going to build off what I just told you, which is the growing importance of ethanol. Well, the implications of natural gas now are not so clear. I showed you before that about half of our energy use in food production is from fertilizers, which is from natural gas. So if that's getting cheaper, you would think that is a good thing in terms of making it easier to produce food at low cost. However, natural gas is also one of the main costs of ethanol production. And you can think of ethanol production as basically converting natural gas into liquid fuel via growing crops and then using natural gas in the processing of those crops into liquid fuel. So as you know, cheaper natural gas, as I just said, or as you know, as of 2 seconds ago, means cheaper fertilizer, and this is just a plot showing that. Not worth going into detail there. But as I said, if you're an ethanol producer and your main costs are corn and natural gas, and your natural gas costs go down, you're willing to pay a little bit more for corn to maintain the same level of profit. Or in other words, you can afford to pay a little bit more. And so if you want to try to weigh the effects of natural gas, well, it depends really what it does to the profitability of the ethanol markets. And the indications are now that it's about, well, I should say we don't really know, but here's just a simple calculation I did, which is that if you want to produce a gallon of ethanol, it takes about 20 cents worth of natural gas via the fertilizer side. Okay, so you're making the fertilizer cheaper, and that makes your corn cheaper by 20 cents. On the other hand, the natural gas required directly for the processing is also about 20 cents, so you have 20 cents more to pay for that corn. So the net effects on food prices overall of this natural gas, I don't want to say explosion, this natural gas increase over time is really ambiguous at this point. And it's one of these things where if you focus on one of these pathways, you can really miss the big picture because there's these other things out there that we haven't really thought about. So to wrap up, I already told you the first 3 points, but in terms of biofuels, we're using about 40% of the corn crop now in the US to provide about 1% of our energy. And this natural gas phenomena is really going to affect food markets in ways that we don't yet quite understand. And my guess right now is they're not going to be as big as they would have been if we hadn't increasingly used food for energy production. And with that, I will take some questions, and then you can all stretch your legs. Thank you. Students first, please. Yes. No, it's okay. You look young. Go ahead.
Okay. Thank you. So I'm actually pretty surprised that 40% of the energy used goes into pesticides and fertilizer. So now my question is to understand, with our current industrialized Monsanto-affected system, currently we're using a lot of fertilizer and pesticides. How is that affecting the energy use? Is it becoming more efficient or less efficient to have, say, genetically modified Roundup and Agent Orange and such?
Okay. Let me answer what I think you asked, and then you can tell me if I didn't answer it. But the use of fertilizer in general, industrial fertilizer, is on net saving a lot of land. We deforest a whole lot less because of that. In terms of a climate impact, it's actually a big benefit. And in terms of energy use, it is a significant amount of the on-farm energy use, but it's saving a tremendous amount of labor, so you would have to look at the energy in the human labor. So I think on net, fertilizer is making us more efficient. Now, in terms of maybe the second part of your question was the Monsanto effect or the GM varieties and how are those influencing our energy use in agriculture. You know, if you look at the two big successful technologies that have come out, one is BT, which is basically eliminating the need for lots of pesticide production, and then you have Roundup Ready, which is also reducing our need for herbicides and at the same time facilitating no-till, which means that you don't have to use as much energy to plow the land, and and you don't release the carbon associated with that for the greenhouse gas effects. So I would have to say, if you look narrowly, if you're grading narrowly on energy efficiency, you'd have to give the modern Monsantos of the world a pretty good record. That's a narrow report card, but that's what you'd have to do. Please. I'm trying to be as provocative as possible this time of day.
Thank you. What do you think of utilizing aquaponics, aeroponics, and hydroponic for, you could localize your food production. For instance, with aquaponics, create about 1 million pounds of food on 3 acres, reduce your footprint, you can do it on buildings or earth, and it can be in any weather, reduce your water consumption, increase yield, and reduce pesticides and herbicide use. Have you looking into that?
Yeah, so this is a question about like vertical farms in urban areas supplying a big chunk of the food demand close to where the food demand is. And I would say that without knowing very much, my reaction is that there's probably a lot of good reasons to do it, and it's probably going to be a good niche market, but you're not going to produce at the quantities at which people consume. In other words, you can probably grow your fruits and vegetables there, but most of our calories are coming from grains like wheat, rice, corn, and we use 12% of the surface of our ice-free planet, sorry, of the land surface of our ice-free planet to grow these things. So to imagine that you're going to build a few buildings in cities and displace that is going too far. But I think there's a proper role for it, and it may well reduce some of the energy use, but it's not going to, I would be very surprised if it transformed our overall picture of agriculture in the world.
One question.
One more? Yes, Stu.
I might be mistaken, but it looked like in one of your plots you were discussing how much energy is required to produce different types of food. And it looked like the amount of energy required to make fresh vegetables was greater than to make beef or pigs or other things. Was I reading that plot wrong, or are the units somehow weirdly skewed so that they are all on the same axes or something like that?
No, you're not reading those wrong. And so vegetables and produce in general are much heavier. They also need to be refrigerated often, or they're frozen and canned, or some combination of those. And that's where the energy comes in. It's really in the processing and that may be a case where eating fresh local fruits and vegetables compared to eating frozen or highly refrigerated fruits and vegetables. That may be a place but I think that maybe the other conclusion to draw from that is how low some of those other things are relative. We've just gotten so good at growing and storing and transporting a lot of these other food items compared to that.
All right, thank you, David.
Thanks.